Okay, folks, this is our fourth video. This is where we get an exponential growth or decay situation that's described in words to us. This slide is in your textbook, and it is on page 81, and most of the problems that I'm going to go through are in that same section. The main thing to remember here is that while the exponential growth or decay equation looks like this, a times b to the x, sometimes we're given this b as a percent change. If that percent change is positive, then it is 1 plus that percent change. If it's negative, if it's decreasing or depreciating, then it's 1 minus that percentage. What's important about writing that percent in the equation is that we don't just write the percent. So if it was 18%, we wouldn't say 1 plus 18. We write the percent as a decimal. So here's our first set of examples. I want you to pause right now and try these examples. Okay, here is my response to these situations. So a house was purchased for $120,000 and is expected to increase at a value at a rate of 6% per year. The first thing that you've got to recognize is that 6% is not 0.6, it is 0.06. So when we write that into the equation, we're going to have to use 0.06 because it is increasing. It is 1 plus that rate. Our starting value is that A, and so I've got 120,000 times 1 plus 0.06 to the x power. Second example, an endangered fox population is 180 and is decreasing by 6%. Again, 6%, 0.06 each month. So this would be 180 as our starting point times 1 minus 0.06 because it is decreasing to the x power. Finally, a car was purchased for $24,000 and is depreciating. There's that big fancy word that just means the value is going down at a rate of 7.3% each year. When we write that percent and we say it's 7.3, we use it's not a whole number of percent. It oftentimes throws kids off and they want to write 0.73. That would be 73%. Just like 6% is 0.06, 7.3% is 0.073. And so again, our equation is 24,000 times 1 minus 0.073 to the x power. Next set of examples are here. A rare bat population was 80 in 2001 and triples every year. How many bats do you expect there will be in 2016? And then we've already done this you try, so we're going to skip that. So do this example at the top. Take a moment and pause so that you get a chance to try it on your own. Okay, here's what I did. 80 is our starting point in 2001. It triples, that means times 3. So 80 times 3 to the x. 2016 is 15 years after 2001. So again, this is 80 times 3 to the 15th power. If you need to type this into your calculator, you will need to type it into your calculator. These are the keys that you'd have to type in. So you type in 80, then hit the multiply key, 3. This sort of caret symbol here means raise it to the power, and then we're raising it to the power of 15. So we get, what is this? This is thousands, this is millions. So this is 1,147,912,560 bats. Ew. We've already done this example. Again, I'm leaving it here so that you have a chance to check your understanding if you decide to do that as one more practice problem. Let's move on. Again, let's talk about these decimal percents. So Here's a problem about the population of China. In 1991, it was 1.151 billion, and it's increasing at a rate of 1.5% annually. Here, I want the exponential equation that models that growth. Second, use that equation to tell me what the population would be in 2001. And then we actually give you the real population in 2001 was 1.273 billion. We'll talk about why those might not be exactly the same. Take a moment and pause the video and try this one on your own. Okay, here's my answer. Again, my starting point in 1991 was 1.15 billion. I'm going to write my equation in billions. I don't really want to write out 1 billion 150 million, and there's the thousands, and I don't want to write that big, huge number out. I'm going to write my equation that predicts my population or models my population in billions. So 1.15 times 1 plus 0.015. That's this 1.5%. It is not 0.15. That would be 15%. There's our equation that models this growth. Now we just have to use it. So 2001 is 10 years after 1991. So we put in 10 for x, plug this into our calculator, and again we get 1.33 billion. Now, 1.33 billion is what our model said. The actual was 1.273. So, when we are looking at models, we sometimes calculate what that error is. We know that it was off by, well, what's the difference there? If we subtract those 0.057 billion off. So that 0.057 out of what it should have been, 1.273, if I divide that, I get 0.045. That means our model was 4.5% off. And in fact, our model predicted it 4.5% too high. So what that tells us is that the actual rate of growth in China during that period wasn't quite the 1.5% that we used in our model. Maybe it was a little bit lower. Here are some SAT questions. You have these in your book. So I wanted to present these so that you could see the answers on those. Again, pretty straightforward on this one. It starts at 4 billion. It's growing by 1.9%. So this first equation looks like the right growth, the exponential growth equation. And then finally, this last one, when we are doubling that biomass, that means we are multiplying by 2. Anything that is multiplying by 2 every year, that is an exponential growth. A linear growth would be adding the same constant every year. Exponential growth is multiplying by the same amount every year. And we know that that exponential growth should look like that characteristic exponential growth curve. That's all I have for today. Make sure that you take the quiz. Have a great day.